Okay, time to get started. So, two quick things before we get back into the math. One is don't forget about the attendance quiz, right? Attendance code disappears in a little less than 2 minutes now. Second of all, I'm very well aware of the temperature in the room, and I apologize. It seems the AC is non-functional at the moment. You can click the switch and it'll start making noise, but it does not put out any cold air. The lecturer that was in here before me had it on the whole class period, and I think it was warmer than it is now. So I think somebody set it to like 90 degrees and then broke it. So anyway, I'll see if I can get that fixed. I have no control over the facilities people, but I'll see what I can do. Okay, so that's why I have the door open, by the way. Hopefully a little bit of the hallway AC will get in here. Okay, so we were talking about the chain rule last time, right? And I gave you a point of view on how to sort of motivate this. You know, why should this be true? And there's various different ways to think about it, and I'm sure they all have their merits. But again, we have a specific goal in mind here. Our goal is not to learn single variable calculus, right? Our goal is to set up a point of view for the single variable chain rule that will extend naturally and conveniently and intuitively to a multivariable calculus setting. That's our goal. And this is the point of view that I think does best with that. So again, the idea is that what a derivative is, right, is something that you multiply by input velocity to get output velocity. That's the point of view that I want to take. And again, there are many others. That's not what we're doing. Okay, so it's a factor, another way to say it. It's the factor that you multiply by that to get that. And this factor point of view is what I think is most valuable. Now, so let's apply that. We've already done this, so I'm going to go quickly through it. The big idea is that, okay, well, the factor that you multiply by this to get that, and the factor that you multiply by that to get this other thing, altogether, you have multiplied by the product of those two factors. So this factor, the purple factor, is green times blue. Right? And then keeping in mind what those factors are, this purple factor is green times blue. And so that the idea that factors multiply ultimately is all that this is. And notice this gives us the single variable chain rule that we've that y'all known for quite some time now. Okay. All right. And now, for whatever it's worth, I like this little point of view down here. Differentiation turns a composition into a product, and you can see the product that we create right here. We're literally multiplying those derivatives. Right? We're multiplying those factors. And why are we multiplying those factors? Well, because we are looking at a derivative of a composition. Z is not immediately a function of x. Z is a function of y. Y is a function of x. So when you differentiate a composition, you get a product. So, okay. All right. Now, let's try to do the same thing in a multivariable setting, and it works super duper well. Again, there's different ways to think about multivariable derivatives, blah, blah, blah. This is the one that's going to fit in, dovetail the best with what we're doing here. And again, just like in the single variable case, the derivative is the factor that you multiply by input velocity to get output velocity. Right, now just for comparison purposes, yes?
Can I backtrack for just a second?
Yes.
The visual you made for 123. I remember you said that whenever partial comes, like u first comes before the second. So why would
yes.
dv dy be in front of dy dx?
Because, in this case, it doesn't matter. These are scalars. You can put them in whatever order you want. I'm doing it in this order because it's going to set up an analogy that works best in the next case where they're not scalars and where the order does matter. So it kind of doesn't matter here is the short answer to your question. Yeah, you're right. Okay. All right. So, so this is the take, right? The derivative, whatever kind of critter that is. Let's not worry about it's a matrix, right? Whatever. It's the thing that you multiply by that input velocity to get that output velocity. And this is exactly the take we had here for single variable. It's just that now these velocities, instead of being sort of one-dimensional velocities, now they are two-dimensional velocities. And by the way, use your imagination. There's nothing about the dimension here that really matters. These could be three-dimensional velocities, or this could be four-dimensional, this could be two-dimensional, whatever. Right? This feature of derivative matrices works no matter the dimensions. Okay, so just like we did over here, I'm going to realize a composition as creating a bunch of velocities of the variables at the different stages and multiply factors. We're going to rip off exactly what we did here. So here we go. Let me zoom in. And by the way, reminder, ignore all the algebra. The equations I have labeled 1, 2, 3, that's just kind of an algebraic take of what I'm trying to convey intuitively. And I think the intuitive take is really honestly the better take. So if we have a multivariable function there, right? The y variables are functions of the x variables. And if I have another multivariable function, here the z variables are functions of the y variables. I implicitly kind of have a composition where I can view the composition as giving the z variables as functions of the x variables. Shameless ripoff, what I did here. And let's think through, what are the various derivatives in these cases? Well, the derivative of f is the thing you multiply by that to get that. It's what you multiply by the velocity in the x world to get the velocity in the y world. Yeah, it's a matrix. Okay, sure. But it's the thing you multiply by something to get something else. It's a factor. Right? So let's think of it as a factor. And the kind of factor it is doesn't change the fact that it's a factor. Let's see here. The derivative of g is what you multiply by that to get that. And then the derivative of the composition is what you multiply by that to go all the way over to get this. And again, factors multiply, right? If you start with this x prime velocity, just think about this velocity here. And I want to ask, how do I get the z prime velocity? Well, I multiply by the green derivative factor, and then subsequently I multiply that by the blue derivative factor. Altogether, I have multiplied by the product of those two factors. And so this purple composition derivative is the product of those two initial factors. And that's all. Let's zoom back out so I can see it all at the same time. That is all that this says. The derivative of that purple composition is the product of the individual factors, namely the individual derivatives. And there you go. This is our first glimpse at the multivariable chain rule. So I have to emphasize, notice how shamelessly, rip off, right? It's a total analog. It's the exact same argument that we gave on the previous page for single variable. It's ultimately kind of the same idea. Again, if you look at it from this very particular, very carefully crafted point of view, same basic idea. Examples incoming. Let's see here. I do want, before I go, I should never erase that. There we go. I do want to address the matter that you brought up a second ago, which is which one acts first and why. Is it left or right, or how does that work? Keeping in mind, these are matrices. Matrices multiply on the left, right? So whatever that vector x prime is, the matrix is on the left, which means the x prime is on the right, and so the the factor that is on the right literally acts first. And it seems backwards, right? Again, that's the tragedy of the notation. But this is on the right because it acts first. You can see in the picture that it acts first. Okay. How we doing? Okay. And we get the same nice little punchline here that differentiation turns compositions. You can explicitly see from how I've written this. We're looking at the derivative of the composition. Taking a derivative turns that into a product. Matrix product here of individual derivative matrices. All right. Okay, now 2 little subtleties I need to point out. Easily, perhaps unnoticed, right? But don't forget, we talked about how the dimension doesn't really matter here, right? There's nothing about the argument, there's nothing about this point of view on derivative matrices that depends on these being 2-dimensional as I've drawn them. I drew them as 2-dimensional because I had to draw something. Right? It's not like I'm using the fact that it's 2-dimensional anywhere. Derivative matrices, they do what they do, no matter the dimensions. If this were 3-dimensional over here, that derivative matrix would be a different shape exactly accordingly. And this always works, independent of dimensions. And so that applies to the chain rule here as well. Any combination of dimensions. Right? So, again, I had to draw something. I drew these as 2-dimensional because it's easy, I guess. It doesn't matter, right? So if this was a 3-dimensional space, exact same argument, exact same matrix equation, the matrices would be different shapes, for sure. But as a matrix equation, nothing happens. Okay. The second little subtlety I need to point out, and this is easily missed. Worse, this is easily mistaken. Again, with the input velocity, right, and the output velocity, and the derivative matrix is the thing that you multiply by. Hey, wait a second, though. This derivative matrix is made up of a bunch of partials. Partials are functions. We need to evaluate this somewhere. Where do we evaluate? Well, if you look back at how we set up derivative matrices and such, it gets evaluated at the point in the domain from which you are moving with whatever your input velocity is. It gets evaluated wherever you are, is the short version. Right? So if you're at the point A in the domain, the derivative matrix is evaluated at that point, wherever that input velocity is coming from. Is that believable? So the subtlety here, where again, this is easily messed up. Let's see, let me do it like so. Let's look at this derivative matrix here. The one that multiplies by the y prime to get the z prime. Notice where we're at is not the point A. Right, well, of course not. A is in a different universe over there. A doesn't even live in Y world. Right? A's got nothing to do with Y world. F of A is where we're at when we say we're moving with velocity y prime. The input to this g function is we're at the point f of A. And so that's why this derivative matrix here is evaluated at f of A. Is that satisfying for everybody? It's easy to mess that up. It was a source of confusion for me when I was first learning calculus, and easy to screw up. Okay. Yes?
So it was a combination of 3. Would the third be like
yes.
an h of g of f of A?
Yes, that's exactly right. Well, whatever the functions, you have to set it up, and the details matter, of course. But yeah, wherever the input to whatever derivative matrix you're looking at, whatever the input is to that function, that point is where you evaluate the derivative matrix. Absolutely. All right. Okay, let's do one. Okay, let's see. I'll zoom a little bit. Here we go. So here is a scenario. Suppose you have two differentiable functions. By the way, notice I didn't give you the functions. Right? I don't want this to be a plug and chug thing. I know y'all are, very, very good at plug and chug, and that's great and all, but we need to understand the underlying ideas, right? So, if only to not make this a plug and chug problem, I'm not telling you what these functions are. Now, I am telling you a couple of things. I'm setting up the sort of the worlds. So there's X world, that's the input to the F function. Then there's Y world, which is the output from the F, which of course means it's the input to the G. Right? That's what it means to compose. What comes out of the first function has to be what goes into the second function. And then there's Z world, which is what comes out of the G function. Okay, so I'm setting that up, and I'm also going to give you for free. Not only are these functions with those variables, by the way, both differentiable. We need that differentiability so the chain rule works. Right? It is that condition that we have to have. In addition to that, I'm giving you that one value of f, and I'm giving you these two derivative matrices. We're not immediately clear why we're being given those, but it's given, so note to self, right? With that. If it comes up that I might need those, I have them. Okay, so the question, two questions actually. First, how do I compute the derivative of the composition? Second, how do I compute this partial? We'll come back to part two. Let's focus for the moment on how do I compute the derivative of the composition. And what I'm going to do is I'm just going to use the formula on the previous page. Right? Here it is. Just copy. Right? Now, you got to be careful about a couple of things. Do be sure that you've got the functions in the right order. You got to keep track of which function is acting first and which function is acting second. As I have this formula written, the assumption is that F is acting first and G is acting second. So heads up on that. That's a really big deal. Conveniently, that seems to be how this is set up as well. You can't count on that. You absolutely cannot count on that, right? By the way, the functions also won't always be called F and G. Right, so anyway, you have to pay attention to which one's first, which one's second. Conveniently, this is exactly as we want it. And so, copying from the previous page, I have this. And then let's see, well, what can I plug into that? I'm going to need to know df at 1, 2. Oh my God, look at that. I already have df at 1, 2. That's just this right here. So, boom. Write that down. Everybody good? Okay, let's see here. Now, I also need dg at f of 1, 2, which I don't immediately see. I have dg at 3, 1, 0. Oh, wait a minute. That is f of 1, 2. Right? So, in fact, because 3, 1, 0 is f of 1, 2, indeed, this thing that I need is something that I have also. Is everybody okay? Now let me show you another landmine. I did this on purpose, by the way. Right? Now, not because I like to be a jerk. I don't. I promise. Right? I do this kind of thing because part of my job is to, when it comes to testing anyway, is to distinguish students that understand and are proficient with the ideas from students who are kind of noticing patterns and sort of copy pasting and praying, right? So the latter is just not an acceptable way to do math. It's just not. Okay, notice what I did. I gave you the matrix that you were going to need to put on the left. I gave it to you on the right. And the matrix that you were going to need to put on the right, I gave it to you on the left. Right? Now, students that are heads up, students that are acting appropriately, understanding the ideas, paying attention to what's doing what, and thinking it through, are not thrown by this at all. Right? You see how we went through and we wrote down exactly what we needed to. We were paying attention to which is first, F or G. We write it down appropriately. and it just falls into place exactly as it should. But if you have a slapdash understanding and you just, you just take these matrices and you just multiply them, you would end up trying to multiply these in the wrong order. Does everybody see that? Yeah, yes?
Wouldn't it be a hint because the matrix dimensions don't multiply?
Correct, but no, that's true, but I can easily arrange it to where they would. Yeah. So what you have there is an observation of how this is not quite as nasty of a trick as I could have made it. Right. But again, it's not nasty and it's not a trick. It's a means of identifying who actually understands the material. Does that make sense? I hope that makes sense. Right. Okay. All right. So heads up. Again, you got to be on the lookout for. Don't just assume that this is going to be. Everything's just going to naturally, and you can just make all sorts of, in fact, inappropriate assumptions. Okay, next question. Next question is how do we compute, wrong color. How do we compute this partial derivative? Yikes. Okay, well, let's see. The partial of Z3 with respect to X1. All right. Well, do keep in mind, this partial is a partial of the composition. Right, the z's are way over here, the x's are way over there. It's by way of f followed by g that we turn the x's into the z's. So this is a part of the derivative of the composition. And good news, I already know the derivative matrix for the composition. It's this. Right, and so what that immediately tells me, this partial derivative that I'm looking for, it's got to be one of these elements. Right? Because that's what derivative matrices are. They give you all the partials. Well, let's see here. Columns correspond to input variables. Don't forget that one, right? Super important. Columns correspond to input variables. We are looking at the first input variable. Therefore, we're interested in the first column. We're looking at the third output variable. Don't forget, output variables correspond to rows. So if you're looking at the third output, you're interested in the third row. And so third row, first column, and you can see that gives me that value right there. Everybody all right? Good deal. Okay, couple of quickies. These are just special cases. I think it's kind of neat to observe that if you only have one input variable, then your original function is actually, it's going to give you a position as a function of one variable. That's a parametric curve, and its derivative is a velocity vector, as we've discussed previously. Furthermore, the composition gives you position in Rm as a function of a single variable. It's a parametric curve, and its derivative matrix is a velocity vector. Right? And so in this special case, what we conclude is that the derivative of this function, right, the derivative of that f, the derivative of kind of the second function, it's what's turning input velocities into output velocities. That is kind of a cute fact. Now, we already knew this. This isn't news. This was one of our this is my sort of favorite physically satisfying interpretation of a derivative matrix. So, old news. But when something you already know is a special case of a more general rule that you've just found out, right? Then it's a reasonable take to say that, this new rule is a generalization of that older idea. So you could say the chain rule is a generalization of this thing that we already knew. It's a take. And again, this example, old news, the derivative matrix is what you multiply by input velocity, which you'll notice was given, to get output velocity, which you'll notice is what we wanted. Right, so there's really nothing new in this example. It's just this could just as well have been a section 2.3 example. Okay. And another special case, and again, this is just a special case. What if, in addition to having only one original input variable, what if you also have only one eventual output variable? Well, what that means, outputs corresponding to rows, means that this matrix has a single row. And that means the way matrix multiplication works, I can rewrite this matrix vector product as a vector-vector dot product. And again, the gradient is the thing that it's if you want to interpret a single row derivative matrix as being a vector, the gradient is that vector. Okay. So again, nothing new, and again, the example that follows is could just as well been from section 2.3. So take a look. It's straight out of 2.3. Okay. Here's a different point of view. I encourage you to think of this as kind of a secondary point of view. I don't think this should be your primary point of view. I think our primary point of view on the chain rule really should be what we have right here. The matrix form. This has meaning, right? I can make a case. It's not even hard to make the case. Each one of these is a factor. Factors multiply. I mean, it just makes sense. It addresses all possible cases of how many dimensions this and that. This is the best way to think about the chain rule. But that said, sometimes it's actually better to think about things in terms of coordinates. These sorts of cases come up. So here's a scenario. I've got f that takes x's and gives out y's. I can talk about its derivative matrix. It's all the various partials of the y's with respect to the x's, blah, blah, blah. Then I'm going to take those y's. G will take those y's and produce z's. Here's its derivative matrix. Again, various appropriate partials of z's with respect to y's. And then I can talk about the composition. The composition will have derivative matrix. That's the partials of the z's with respect to the x's. So nothing new. I'm just writing it down. This is the matrix form of the chain rule that just sort of expanded in coordinates. And now let's just notice, nice little observation here, that if you should happen to be interested only in a particular one of the elements of that composition, right? If you just need to know one partial derivative, which actually happens, this is not rare, this is fairly routine. If you only need to know that one partial, I don't need to compute the whole matrix, right? All I need to compute that element, well, I'm gonna need to know the corresponding row in this matrix, and I'm gonna need to know the corresponding column in that matrix, and I'm gonna have to dot them in the usual way. Right, but that's all I really need in order to compute that entry. I don't need to know any of those elements or these elements or any of these elements or those, whatever. I don't need any of that. I don't need to be multiplying out and finding all this other stuff that I just don't care about. Is that cool? So this is a nice sort of secondary. I like to think of this as a secondary formula. This is presented in a lot of books as the multivariable chain rule, and again, it has its moments. Anyway, I like to think of the second version of the multivariable chain rule. It's just matrix multiplying what we already knew. Okay. Now, again, you got to be aware that the variables will not always be named and ordered exactly as we have here, and the functions will not be named F and G, and they won't necessarily be in that order. So we have a problem with the question of how we're going to keep track of which variables are playing what rule, and therefore which partials multiply. I mean, you can see there's a lot of potential for messing this up. We'll talk about that in a minute. So I do want to point out a nasty landmine that has revealed itself now. And that is when you start writing this down, okay, I want this partial, and you write down, okay, it's equal to, well, this times this. You might pause and think, hey, wait a minute. Doesn't that cancel with that? And doesn't that leave the numerator what I want it to be? And doesn't that leave the denominator what I want it to be? Maybe this is it. Maybe we stop there. Maybe this is the entire multivariable chain. Or maybe this is a bunch of garbage. Yeah? No, that's wrong. We know it's wrong because we just derived that formula. That stuff that I just crossed out it's there. That's how matrix multiplication works. We know that this isn't right. And yet we have I'm going to say, alluring line of reasoning that kind of makes it look like it ought to be right. Really not clear what we've done wrong here. Does everybody see the confusion? So I'll tell you what we've done wrong is that we have fallen for the very unfortunate suggestion created by this notation of writing partial derivatives as fractions. We've fallen for the terribly tempting but untrue suggestion that that's a thing. Partial y1 by itself is not a well-defined thing. It means different things in different circumstances. And that's ultimately the problem here. When I said that, oh, hey, check it out, these cancel. No, they don't. They're not the same thing. Very importantly, not the same thing. Let me elaborate on what I mean by these not being the same things. And just for convenience, I have this term written down here. Let's think about what this partial y1 is. That partial y1 is part of a story. In this story, I'm doing a computation that has certain sort of implicit suggested, assumptions. In particular, when I say partial with respect to y1, this scenario requires that all of the other y variables be constant. That's the scenario that we're looking at when we write this down. All those other y's are not allowed to change. Now let's look over here. This scenario, this story where I compute this partial derivative. What's going on in this story? In this story, there's a whole bunch of x variables, most of which are going to be constant, but then I'm going to allow myself to change xj. And then as xj changes, that's going to start causing changes in y1, but it's also going to start causing changes to all the other y variables. Right? So in this scenario, this partial y1, this partial y1 is a player in a story where these y's are not constant. They're importantly not staying constant. Xj is changing. They are functions of xj. They will be changing and not constant. So the suggestion that, I'm sorry, I could have sworn I had that off. Oh, I did have that off. Sorry, I don't know how to operate my phone, apparently. So these things, think of them as two characters, both named Steve, but in different books, right? And if you've got a Steve in, I don't know, is there a Steve in the Harry Potter books? I don't know. Okay, probably not. Anyway, Okay. If there's a Harry in the Harry Potter books. Maybe there's a Harry. Oh, there's a Harry in. My daughter was just watching Spider-Man. Isn't there a Harry in Spider-Man? I think. Yeah, they're not the same. Right? I mean, same name, not the same people. And likewise, these are just straight up, full on, not the same. You cannot cancel them. And when we were over here saying, yeah, we'll just cancel those, and oh my gosh, it works, garbage. Everybody on board? Okay, so this is a dangerous, dangerous landmine that is easy to step on. Please do not step on this landmine. I make a big deal out of this because every year there's a certain fraction of students who will write this down and compute from that. And it is absolute nonsense. Okay. Alrighty. Now, how do you keep this all straight? And again, what if the variables were named something different? How do I know that which differently named variables are playing what roles and therefore go where in this equation? Here's the way I like to think about it. I strongly encourage you to do the same. We have these sort of three separate worlds. I'm listing here only the variables because it's the variables that I want to make an argument about. Let's imagine that we're taking a partial with respect to xj. Here's xj. That means that all the rest of these are well, let me just do it like this. I'll just, all the rest of these are constants. Well, what happens? What happens when you start fiddling with xj? Xj starts to change a little bit, and well, that means all of these y variables are going to be changing. And each one of them, individually, let's just look at y1. As y1 changes, that will cause some contribution to how zi changes. But here's the thing. So y2 is also changing. As y2 changes, that will make an entirely separate, independent contribution to how zi changes, etc. So we can trace these along. I claim that for each path, which you'll notice corresponds to what we're going to call an intermediate variable, because it's in the middle. And for each one of those paths, I can talk about, okay, well, as changes propagate along this path, given how much xj is changing, what does that mean about how much y1 changes? And given how much that changes, what does that tell me about how much zi changes? And again, we have these factors. And let's see here. The factor by which xj changes turn into y1 changes. Is that partial? The factor by which y1 changes contribute to zi changes is this factor right here. And so altogether, factors multiply. This term corresponds to that path, which corresponds to y1 as an intermediate variable. Everybody buying it? So this is the beautiful thing about it. Let me show you what the sort of the interpretation punchline is. For every intermediate variable, there's a corresponding path and therefore a corresponding term. The intermediate variable always goes there and there. It's always the same. Whatever it is that you're taking the partial with respect to will always be there. And whatever it is that you're taking a partial of will always go there. That's the pattern. For every intermediate variable, you get a term that are always structured like this. This is a great way to keep track of stuff. Let me show you an example of how we can do this. So here's a question. I'm going to compute this partial derivative right here. Now again, I didn't give you. I guess I did. I gave you the explicit function here. We're going to do this using the multivariable chain rule. By the way, yes, I could take the outputs from the f function and plug them into the g function and turn this into a great big single variable function where z2 is explicitly a function of x2, that would defeat the purpose of the question, right? And let me remind you, there's some discussion of this on the class webpage, the class website, that rather than me making unnaturally awkwardly phrased questions to the goal of allowing only one possible solution, namely the one that gives me the demonstration of your proficiency that I need, right? I shouldn't have to craft a awkward, weird question to avoid what I think should be clear, which is demonstrate the proficiency that we're looking for, right? On an exam, if there's a question like this and it says compute this partial derivative, if you plug in and make it a single variable function and use single variable calculus, you have not done what the problem is about. Again, keep in mind, it's not about answers. The fact you got the right answer is not the point. That's not what this class is. That's not how grading works, right? This is discussed at length in the class website. Your job on an exam is to look at a question like this and say, okay, well, what's the purpose of this question? What proficiency is this question wanting me to demonstrate? Identify what that proficiency is and then give it to me. Right? Does that make sense? Okay, so let's see here. I advise, I think I'm a big fan of the following. You should always draw yourself a diagram representing which variables are where. Yes?
Quick question.
Yes.
Why do we have to account for every single, y variable?
Yeah.
If we wanted to get from x2 to z2, then can't we just simply take one, y version?
Yeah, no, I hear you, but that's equivalent to the argument that this one term is all you need.
Okay.
You see what I'm saying? It's not true. So the reality, from this point of view, the take would be that, what's happening along this path, that's just one part of the story.
Okay.
Right? Imagine if, I'm just going to make up some nonsense here, but so play along. This is a poor analogy, but this is things that I can do, and this is my bank account, right? And if I do stuff, well, that might cause a lot of consequences. It might cause this person to say, "Hey, good for you," and he gives me $100. But that same action might cause a bunch of people to decide to give me money. Wouldn't that be nice? But my point being that there's a lot of different paths along which that can be consequences of XJ changing.
Okay.
See what I'm saying?
Yeah.
And you've got to account for all different ways that XJ's changes can propagate over and cause.
And then you add them all together to account for all the changes in the
Yes. That's right. And so, and literally there are only so many paths that exist that you have to worry about. Yeah. Okay, so draw your diagram. F that takes X's and gives Y's is there. G that takes Y's and gives Z's is here. I now have a diagram that shows what influences what. The question says, as X2 changes, how does Z2 change? And how many different paths are there? Well, there's a path through the intermediate variable y1. And here's my y1 term. Right? And then there is a path through the intermediate variable y2. Here is the y2 term. Is that cool? So I didn't have to rely on having memorized a formula back there. I have givens, I draw the diagram, and I write down the natural consequence of just thinking about the paths. This point of view does the bookkeeping for us. So really nice. Okay, real quick, don't confuse your variables. It's super easy to do. This single variable calculus example here, I'm sure you all can at a glance look at and see what's wrong with this analysis. The problem is I didn't evaluate G prime f of x like I should have, right? See, this needs to be f of x, and up here I didn't plug in f of x. I just used x, and so I get a laughably wrong answer. Single variable calculus. I know y'all know that, but you know what? There's a much easier way to think about this, right? Ultimately, even this, something really terrible about how this is written. This is working with functions set up and written in terms of a confusion of variables. That's no good. Look, if f is a function of x, what am I going to call the thing that comes out of f? I don't think I should call it x. X is the input. If I called the output x also, that would be silly at best. Kind of unacceptable, really. Well, keep in mind, what comes out of f is what needs to go into g. So you can't write g as a function of x. You got to write g as a function of, well, something else, whatever you decided to call the output from f. Right? So I think this whole thing up here is nonsense. And what we should do is just rewrite g. Now this is the same g. It's the same function. I've just got it written in terms of a different dummy variable so as to avoid a confusion of variables. And now I've taken a scenario that came to me, I'm just not ready for analysis, right? And I've written it in a way that now it makes total sense. So now, again, I know y'all know single variable calculus. Just let's take a moment to appreciate how easy the calculation becomes here. I can be as sloppy as I want at this point about how I write, a derivative of a composition as a product of the derivatives, and I didn't put the g prime of f of a. I left that out. Oh my gosh, right? But no problem, because g prime being 3y squared, it's written in terms of y. And it naturally then comes up that, hey, wait a minute, what is this y? Oh yeah, y, the thing that goes into g, is what came out of f. It's x squared. And you plug in y equals x squared, and boom, there you go, you get the right answer. So if you don't confuse your variables, the variables do some bookkeeping for you. The variables will help you. If the variables are set up right, there will be no landmines to step on. So you don't have to remember not to step on them. I think that's a good idea, right? If you have two ways to get from A to B and one of them is through a minefield, let's go the other way, right? Okay. Same thing comes up in multivariable. It's a little bit more sneaky in the multivariable setting because you're keeping track of various other things. There's matrices and derivatives. Oh, wait a minute, which one's a constant, which one's a variable, partial derivatives. You got to keep that straight. And all these other things going on, and it's easy to accidentally forget to plug in, at the end when you're supposed to. So just avoid the situation. Notice again, two functions have come to me. Perfectly good functions, not a thing wrong with them. Until it is suggested that I should compose them, and once it's suggested that I should compose them, hey, listen, what comes out of f? I really can't call those x and y, and so therefore what goes into g, I really can't call those x and y. That doesn't make any sense. That's an accident waiting to happen, right? So all you do, rewrite exact same function, different dummy variable. Plural, different dummy variables. Right? And then the different dummy variables do your bookkeeping for you. There's no landmines. Go ahead, proceed, take the various derivatives, yada, yada, yada. And then at the end, you'll find yourself naturally looking at something like this and then realizing, oh, well, I need all of this in terms of x and y. So, hey, wait a minute, what is the deal with u? What is u? Where did u come from? U was my first input to the g function, which means it's my first output from the f function, which means it's x squared plus y squared. So you just plug that right on in. The variables did your bookkeeping for you. Does everybody see how that works? So heads up on that. Try not to confuse your variables. This is a good place to draw the line. See y'all later. Have a great weekend. Okay. Oh my gosh, so hot in here.